In this series of videos, I'm going to be learning the Rust programming language. Now, full disclosure, I have learned some Rust before, but it's been 18 months since I've touched any Rust code, and I want to get back into it. And a lot of my students ask me, how do I learn a programming language? Rather than me telling you, you can watch as I do. So, this is how I do it. I've got my AI open. I've got a whiteboard in case I need to take any notes. And I've got two books on Rust. Okay, the first is conceptual, tells you about concepts, tells you how everything works. The second is for code snippets, in case I need reminding of syntax. And on the right hand side here, I've got a bunch of exercises which I'm going to go through. Okay, so first exercise. I don't think there's anything to do here. I think it's just move on to the next one. Okay, second exercise. It says fix the code to print hello world. So I already know how to print in Rust. I remember this. It's print ln is the macro, and I think we're done. Now, if I didn't know how to do that, I can go into my code snippets book and take a look, and there it is, print ln, print the text to the console, and that's done. Okay, let's move on to the next one then. The next one is variables. So the README tells me where in the book to find it. Chapter 3, page 1, variables and mutability. So let's go to the book, Rust Programming Language, Chapter 3, page 1, variables and mutability. So we could read through all this, mention storing variables, values of variable section, default variables are immutable. Okay, so this is kind of interesting about Rust. Rust, all variables are immutable until you make them mutable using a mut keyword. It's slightly different to other programming languages, where, like when you let x equals 5 in another programming language, like normally, it will be mutable, means you can change it. In Rust, you can't do this. You can't change the value of x once you've defined it. If you want to, you have to use the mut keyword. Like there it is, mut x equals 5. As mentioned in the storing values with variables section, by default, variables are immutable. Immutable, you can't change. This is one of the nudges Rust gives you to write your code in a way that takes advantage of the safety and easy concurrency that Rust offers. One of the key points about Rust is memory safety. However, you still have the option to make your variables mutable. So you can make them mutable, you can make them changeable. Mutable means changeable, they can be changed. Let's explore how Rust encourages you to favor immutability and why sometimes you might want to opt out. When a variable is immutable, so when it cannot be changed, once a value is bound to a name, you can't change it. To illustrate this, generate a new variable. Well, we're not going to do that. You can walk through their projects and they teach you how to do it. I'm going to do the exercises instead. So it gives you this. It says, here's a function, let x is 5, print out the value of x. Now change x to 6 and print that out. Now this function I know will fail. So when you run it, you'll receive an error message regarding the immutability error. Okay, cool. This shows here, and Rust errors are actually quite good. They tell you what's wrong and they give you some help to fix it. So it says, hey, you can't assign twice to an immutable variable x. So assign means x equals something. X equals something. We're assigning it twice. Can't do that. And then it gives you help. It says, hey, why don't you make it mutable? Let mutable x equal 5. And if you do that, then you can reassign it. This example shows that the compiler helps you find errors in your program, so the Rust compiler is actually quite good. It tells you quite a bit about what's wrong. So here it tells you where the error is, and in some instances it even gives you some help on how to fix it. You receive an error message, cannot assign twice to a mutable variable x because you tried to assign a second value to an immutable x variable. It's important that we get compile-time errors when we attempt to change a value that's designated as an immutable, because this very situation can lead to bugs. It can. Oh my god, this kind of thing happens in JavaScript all the time. Where are we? Lead to bugs. If one part of our code operates on the assumption that a value will never change, another part of our code changes that value, it's possible that the first part of the code won't do what it was designed to do. Exactly that. The cause of this kind of bug can be difficult to track down after the fact. That is true, especially when the second piece of code changes the value only sometimes. So yeah, it may not change it all the time. It may be changing it due to specific conditions. The Rust compiler guarantees that when you state that a value won't change, it won't change. You don't have to keep track of it yourself. That's great. So in another language, let's use JavaScript. You have to track the variable if it changes or not. Whereas in Rust, the compiler does it for you because it cannot change. If you use your mute keyword, then it can change. But if you don't change it, the compiler will tell you, hey, remove the mute keyword. So the fact that it has a mute keyword means it's definitely changing. That's a very important point. It's not optionally changing. You don't use mute just because you think you might change it. You only use mute when it changes. If it doesn't change, the compiler won't compile. It'll tell you to remove it, which I think is brilliant. Your code is thus easier to reason through. Great. But mutability can be very useful. This can make your code more convenient to write. Although variables are immutable by default, you can make them mutable by adding the mut, whatever you want to say, in front of the variable name, as in chapter 2. We haven't read chapter 2, that's fine, I've skipped after that. Adding mute also conveys intent to future readers of the code by indicating that other parts of the code will be changing this variable's value. That's important. So if I'm picking up some code that somebody else has written, if it's got that mute keyword, I know straight away that that is definitely changing somewhere else in the code. So here's the same example. And now this should work because you've created a variable, it's mutable, use the mute keyword, and you set it as 5. It prints out that it's 5, then you change it to 6, and then it prints out that it's 6, and you're allowed to change it. If you don't change it and use the mute keyword, like if you didn't have this line, but you still have the mute keyword, it won't compile. The compiler will tell you, change it or remove the mute keyword. So it's one or the other, not both. So we run the program now and it works. Prints out that it's 5, prints out that it's 6. We like that. We're allowed to change the value bound to x from 5 to 6 when mute is used. Ultimately, deciding whether to use mutability is not up to you and depends on what you think is the clearest in that particular situation. See, it depends on what you're trying to do, essentially. Generally, we prefer immutability. We only use mute when we have to. Constants. Like immutable variables, constants are values that are bound to a name and are not allowed to change. But there are a few differences between constants and variables. So in this case, constants are like variables, but there's no way of changing a constant, so you're not allowed to use a mute with a constant. This is for things which we know aren't going to change. So for example, if I'm building a clock app, which needs to know how many hours and minutes and seconds, needs to do that calculation. So it counts up the seconds, and then it works out how many hours, minutes, and seconds that is. So it's going to do a divide by 60 and then a divide by 60. So that 60, knowing that there's 60 seconds in a minute, I can save that 60 as a constant. I can say seconds in minute equals 60. I know that's never going to change. That's going to be a constant. So I can say const seconds in a minute equals 60. There's no reason to change that. Okay, so let's keep going. First, you aren't allowed to, there it is. You aren't allowed to use the mute with constants. Constants aren't just immutable by default, they're always immutable. You declare constants using the const keyword instead of the let keyword. Now, this is kind of similar to other languages, things like JavaScript, where you have a let and a const and a var. And generally, I've seen more modern, when we're working with TypeScript, we generally tend to use const for everything. Because we like this. We like the fact that things are constant. There's less chance of them breaking. And the type of the value must be annotated. Okay, so this is important in Rust, that if you're going to use the const, you have to define the type. So there's no way of inferring it in Rust. Rust does infer, but not for const. So for example, the const that I was talking about, if I was using a seconds in a minute equals 60, I would have to define the type. I would say, hey, it's a unsigned 32-bit integer, U32. We'll cover type. Okay, we're going to do type annotations in a different section. That's fine. Don't worry about details now. Just need to know whatever. Okay, cool. Constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of the code need to know about. Okay, so that tells me that constants have scope. So if you're defining a constant, you have to think about the scope in which it lives. That's fine. Put them in global scope, they can be seen everywhere. You give them a defined scope, they will live for, no, the lifetime of that constant will be for that scope. Okay, that's great. The last difference is that constants may be set to only a constant expression, not the result of a value that could only be computed at runtime. Okay, so you can't make a constant equal to something that needs to be worked out based on a value that is not known. So for example, okay, so here's their example. 3 hours and seconds. So they've created a constant for the number of seconds in 3 hours. And they've done the calculation. So this calculation can be worked out at any time. It can be worked out at compile time because it has all the numbers. So we're allowed to do that. But let's say we wanted one for, I don't know, user-defined hours. So we don't know how many hours. We want the user to type that in. That can't be a const because we don't know that in advance. So a const, you have to know everything in advance. So you can't do a, hey, user input, and then we'll create a const out of that. You cannot in Rust. In Rust, you have to know all the bits that you're calculating for your const in advance. And this is a good example of a const because the number of seconds in 3 hours is never going to change. That's a fixed value. That value will never change. And I like how they've done the calculation here because if you're using just the, like, you could just say the number like 60 times 60 times 3, 3,600 times 3, is it 10,800, I think? But that has less context. This gives me a lot of context. So it's like 60 seconds times 60 minutes times 3 hours. When I read this, I know a lot about it. If it was just a whole number, I don't know anything about it. Okay, so the const name, 3 hours and seconds, and its value is set to multiplying 60, 60, and 3. Number of hours we want to count in this program, cool. Rust naming convention for constants is to use all uppercase with underscore between the words. Okay, so, right. So it's like uppercase with underscores for the spaces. Cool. So that's how we, and again, naming conventions are rules. They're not like, the code will still compile if I don't do that. But it's good to use the naming conventions because when other people are reading your code, it will make sense to them because we're all using the same conventions. Compiler is able to evaluate a limited set of operations at compile time, which lets you choose to write out the code in a way that's easier to understand and verify, rather than setting the constant to, okay, so this is basically saying what I was saying. But don't set it to 10,800, because 10,800 doesn't mean anything to somebody reading it. Or if somebody reads this, they're going to think, hey, that's seconds, that's minutes, and that's the number of hours. Really easy. And the compiler will calculate that. We don't have to do it for the compiler. Constants are valid for the entire time the program runs within the scope in which they were declared. Okay, so exactly. So if they're in global scope, they will live while the program's running. If they live within a particular scope, like if they're declared inside a particular scope, they'll live for that scope as long as the program's running and they're in scope. I think property makes constants useful for values in your application domain that multiple parts program might need to know about, such as the maximum number of points any player of the game is allowed to earn, or the speed of light. So if you're making a game and the highest possible score is 50 points, that's a good thing to put in global scope. Max score 50. Or if you're doing some kind of science program and you need the speed of light, again, that's a great thing to put in a constant speed of light. Naming hard-coded values used throughout the program as constants is useful in conveying the meaning of that value to future maintainers of the code. Well, that makes sense. So if the speed of light, I think it's 2.97 times 10 to the 8 meters per second. If I kept writing in 2.97 times 10 to the 8 meters per second everywhere that I use it in my code, it doesn't really mean anything to somebody reading it. It's just numbers. Whereas if I declare this const speed of light equals 2.97 times 10 to the power of 8 meters per second, then use that speed of light, it makes a lot more sense to whoever's reading my code. Because now I just put the variable name, the constant name, speed of light, wherever it's used. Another person reading my code makes a lot of sense to them that, hey, that's the speed of light. Okay, shadowing. This is a bit weird. Okay, shadowing, I remember, is a bit different to how other programming languages work. Okay, chapter 2, declared new variable, whatever. Rustaceans, people who write Rust code, say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see when you use the name of the variable. In effect, the second variable overshadows the first, taking any uses of the variable name to itself. Either it itself is shadowed or the scope ends. We can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. Okay, so this is a bit strange. So I've gone let x equals 5. Now, we did say that we can't redeclare a variable. Here, we're not redeclaring it. Here, what we're doing is we're creating a new variable, also called x, which kind of sits on top of this one. Like, if we think of it like layers. And we're saying it's the previous x plus 1. So the old x is still there, but the new x is x plus 1. And now we've created a new scope, so scope is some brackets. And we're creating another x, which is x times 2. So first it was 5, now it's 6, now it's 12. So this will print out 12 first. The value of x in the inner scope is 12. That's what it will say. Now that this scope here is closed, we close that bracket, close of scope. This layer of x is removed. And we drop down to this previous layer of x. So this goes away, and we go back to this one, which was 6. So now it will print out the value of x is 6. So it'll do this one first, it's 12. Then it'll do this one next, goes back to 6. So the program first binds x to a value of 5, then it creates a new variable x by repeating let x equals the original value and adding 1. So the value of x is then 6. Then, within an inner scope created with the curly brackets, the third let statement also shadows x and creates a new variable, multiplying the previous value by 2 to give x a value of 12. When the scope is over, the inner shadowing then ends and x returns to being 6. Remember the program, we get this. So first it says it's 12, then it says it's 6. So yeah, exactly that. So it makes it 5, then makes it 6. Then for these brackets, because we have a set of brackets, it makes it 12, prints out that it's 12, and then sends it back to being 6. That 12 only lives for these brackets. So it goes back to being 6 and then prints out 6. So 12 and then 6. Nice and simple. Shadowing is different from marking a variable as mute because we'll get a compile time error if we accidentally try to reassign to a variable without using the let keyword. By using let, we can perform a few transformations on the value, but have a variable be immutable after those transformations have been completed. The other difference between mute and shadowing is that because we're effectively creating a new variable when using the let keyword again, we can change the type of the value, but reuse the same name. Now that's kind of interesting there. Naming variables is a whole thing. Everybody has an opinion on it. Every company has their own way of doing it. There are some standards, but naming variables is always a difficult thing. And sometimes you run out of names. So this process here allows you to reuse a name and also change its type. If, let's say, you're never going to use the previous version of that, you want to create a new version of the new type of the new thing, you can reuse that name. So here's an example. I like this example. So for example, our program asks the user to show how many spaces they want between some text by inputting space characters. So let's imagine that we've asked somebody to type this in. We want to store that input as a number. So we let the person type it in, and we save it in this variable called spaces. But we don't really care about the spaces themselves. We want the number of spaces. So we've got their spaces. So then what we do is we take let spaces, create a shadow, and we get the number of those, the length of that. And now that spaces refers to the number of spaces rather than the actual spaces. This is a great example. So the first spaces variable is a string type, and the second spaces variable is a number type. So this is a string. String is just characters. And the second one here is a number because we're counting the length. That dot len does a count of how many spaces there are, let's say. Shadowing thus spares us from having to come up with different names such as spaces str and spaces num. Oh my god, I've seen this so many times, it's crazy. Instead we can reuse the simpler spaces name, and that makes a lot of sense because if we're never going to use this, if we only really need this actual spaces to work out how many spaces there are, this allows us to shadow it and then reuse the spaces variable. So we can reuse the simpler namespaces. There we go. Okay, cool. However, if we try and use mute for this, as shown here, we'll get an error. Now, we can't make it mutable, because to make it mutable, it will have to stay as a string. We don't want the string. We want a number. Okay, so if it was mutable, this would fail, because this is a string, this is characters, and this is a number. I like the Rust errors, they're great. So we made it mutable. And it tells you what's wrong. It's expected a string, but found a usize. Usize is a number, unsigned number. And we're expected a string. Now we've explored how variables work, making with data types. Okay, so let's go back to our exercises. I'm going to do the exercises now. I think I've got enough information to do the exercises. So add the missing keyword on this one. So the missing keyword here, I think, is the let keyword. Because we're defining some variable. There we are. We define a variable x equals 5, and you can see that there. It's inferred the type. I haven't typed that I32. I probably wouldn't use an I32. I'd probably use a U8 for that one. So U8 uses less memory, essentially. But we're allowed to let Rust infer that from there. Okay, brilliant. Let's see how it's done. Hey, we got it right. Next. Okay. Variables 2. So to do, change the line below to fix the compiler error. So we've got x equals 10. Okay, so we can just define it. Let's make it 10. So we defined it. So if x is 10, x is 10. So if we go to the output, let's see what happens. There it is. X is 10. Nice and simple. If we change it though, let's see if that output changes. Let's make it 7. So x is 10. Nope. So go here. Else x is not 10. X is not 10. Nice and simple. Okay, next one. So we're on variables 3. Okay, change the line below to fix the compiler error. So we've got x, and it's defined as an I32, which is an assigned 32-bit integer. Signed is positive, negative. And it's trying to print it out. I think the problem here is that there is no value. Let's make it 8. Done. Output number is 8. If we change it, that output should change. 42. Output is 42. Nice. Variables 4. So fix the compiler error. So let's have a look what the compiler error is. First assignment x. Consider making it mutable. Cannot assign to. Okay, so this is the mutable error. So let's take a look at it. So this line here, x is 3. It prints out 3. Then I want to change it to 5. So and it also tells me don't change this line. So part of the exercise is to not change this line. Okay, so a bit of a hint here. Don't change that line. So I have to make this mutable to allow it to be reassigned as 5, and then it prints out 5. So it should print out 3, then it should print out 5. There it is. Number is 3, number is 5. Brilliant. Next. Okay. We're on a roll. Variables 5. So we got this number and okay, so it says it's number because that's the name of the variable. Remember, the name of the variable doesn't really mean anything. It's just a name attached to the thing that we're saving. So in this case, we've named the variable number, but we've given it like a string, which is this. And Rust has inferred the type here, static string. Okay. And then we're printing, spell this number, okay. And also, part of the hint is don't change this line. Okay, so I'm not allowed to change that line. Then it says number is 3, and print this out. Okay, so I think this is the shadowing, because actually, I'll explain why. So this number here, what is called number, is written as a string, 3. Whereas number variable here, called number, is now a number. So I think because they're different types, one's a string, one's a number, we need to shadow it. Okay. Brilliant. That's done. And variable 6, last one in variables now. Change the line below to fix the compiler error. So const number equals 3. Print number. Okay, so I think we read that constants must have a type. This one doesn't have a type. And Rust isn't allowed to infer it from a constant. Look at our previous ones, Rust was inferring it. Rust was working out the type from the value that we gave it, whereas it's not allowed to do that for a const. So we're going to have to define it. We'll go, I don't know, let's say U8, because it's only 3. There we are. So we've completed the variables chapter. We're going to stop there. We're going to do the functions chapter next time.